In this video, we're going to learn how to rationalize the denominator. Let's start with this example. 1 over the square root of 2. What do we mean by rationalizing the denominator? Rationalizing the denominator means to make the denominator rational. The square root of 2 is not rational. It's irrational. Because we can't simplify the square root of 2 to an integer like the square root of 4, which is 2, or the square root of 9, which is 3. In other words, rationalizing the denominator means to make the denominator free of roots by getting an integer as a solution in the denominator. The square root of 2 is equivalent to 1.41 and so on. The number is not periodic and never ends, so it's not an integer. So we want to get it out of the denominator. But how can we remove the square root of 2? Before I tell you that, I want to say that when multiplying 1 over the square root of 2 by 1, the value of the expression does not change at all. 1 divided by the square root of 2 times 1 is still 1 over the square root of 2. So instead of multiplying the expression 1 over the square root of 2 by 1, we could also multiply it by the square root of 2 over the square root of 2, right? This is because the square root of 2 over the square root of 2 is also 1. So you're not actually changing the value of the expression. We multiply fractions by multiplying the numerator by the numerator and by multiplying the denominator by the denominator. 1 times the square root of 2 is the square root of 2. But what is the square root of 2 times the square root of 2? If you're unsure, feel free to watch my video about the laws of roots. We can write this as the square root of 2 and that raised to the power of 2. To see that the square root and the power of 2 cancel each other out. Now we've turned an irrational denominator into a rational denominator without changing the value of the original problem. How cool is that? Let's look at another example. 3 over the square root of 5. Again, we multiply the numerator and denominator by the square root of 5. The value of the original expression does not change because the square root of 5 over the square root of 5 is the same as multiplying the original problem by 1. In the numerator, we get 3 times the square root of 5, which we leave as is because we can't simplify it. The square root of 5 times the square root of 5 is 5, which is a rational number which is what we wanted. What about x over the square root of 3 plus x? Again, multiplying the numerator and the denominator with the square root of 3 plus x. Gives us x times the square root of 3 plus x over 3 plus x as our solution. Let's look at this example. 2 over the third root of 5 to the 7. Can we solve like we did in our previous examples with just multiplying the numerator and denominator by the third root of 5 to the 7? Let's try it the same way we did in our previous examples. What is the third root of 5 to the 7 multiplied by itself? According to the multiplication rule for roots, we get the third root of 5 to the 7 times 5 to the 7. And according to the multiplication rule for exponents, we get 5 to the 14 under the root. This didn't bring us any closer to our solution. If we had a 3 instead of 14 in the exponent, we would then get the third root of 5 to the 3. Which would just give us 5. Which is a rational number. But how can we get a 3 instead of a 14 in the exponent? We just have to subtract a 4 from the 7. Which we can do by multiplying 5 to the 7 with 5 to the negative 4. So the third root of 5 to the 7 multiplied with the third root of 5 to the negative 4 leads us to the third root of 5 to the 7 minus 4, which is 3. And the third root of 5 to the 3 is 5, which is rational and which is what we wanted. Let's do another example similar to the previous one. 3 over the 4th root of 5 to the 6. How can we get a 4 out of the exponent 6? Feel free to pause the video and try this yourself. We just have to subtract 2 from the 6, which we do by multiplying the 4th root of 5 to the negative 2. So the 4th root of 5 to the 6 times the 4th root of 5 to the negative 2 is the 4th root of 5 to the 6 minus 2, which is then the 4th root of 5 to the 4. Which becomes then finally 5. So we get 3 times the 4th root of 5 to the negative 2 over 5. But maybe we can also simplify the numerator further. According to the converting roots to exponents law, we can write the 4th root of 5 to the negative 2 to 5 to the negative 2 over 4. After cancelling out the 2 and 4, we get 5 to the negative 1 over 2. After using the rule for converting exponents to roots, we get the square root of 5 to the negative 1, which we can write by using the rule for negative exponents as the square root of 1 over 5. By applying the division rule for roots, we can distribute the root to the 1 and to the 5, and we get the square root of 1 over the square root of 5. The square root of 1 is 1. And 3 times 1 is 3. We divide fractions by keeping the top fraction as is and multiplying with the inverse of the bottom fraction. So we get 3 over the square root of 5 times 1 over 5, which leads us to 3 over 5 times the square root of 5. So once again, we have an irrational number in the denominator, which is exactly the topic of this video. So feel free to pause the video and think about how to remove the square root of 5 to make the denominator rational. We just have to multiply the top and the bottom of the fraction with the square root of 5. So we get 3 times the square root of 5 in the numerator and 5 times the square root of 5 times the square root of 5 in the denominator. The square root of 5 times the square root of 5 is 5, which is a rational number, which we wanted. After multiplying 5 with 5, we finally get our answer to the problem, which is 3 times the square root of 5 over 25. Let's look at this example with the same type of problem. 7 over the 5th root of 2 to the 3. Again, we can make a 5 out of the exponent 3 by multiplying by the 5th root of 2 to the 2. So the 5th root of 2 to the 3 times the 5th root of 2 to the 2 gives us the 5th root of 2 to the 3 plus 2. Which then gives us the 5th root of 2 to the 5. Which finally gives us 2. So we get 7 times the 5th root of 4 in the numerator. The denominator is rational with the 2, and we are done with this problem. Let's do one last example with this kind of problem. 2 over the 3rd root of 4x. Again, the question we have to ask is, how can we remove the 3rd root? We saw in our previous examples that the 3rd root disappears when we raise the expression under the root to the power of 3. But what is a power right now under the root when we don't see any power? Remember, when there is no power, it is equivalent to the power of 1. And also make sure to put the whole expression, which is 4x, in parentheses, and raise that to the power of 1. So to get a 3 out of the exponent 1, we have to multiply the 3rd root of 4x with the 3rd root of 4x to the 2. Because 2 plus 1 equals 3. After cancelling the third root and the exponent 3, we get 4x in the denominator. Now we can cancel out the 2 and the 4. And we get 2x in the denominator. Let's move on to the next example, where we have the sum of a root and a number. 2 over the square root of 2 plus 1. Can we solve this the same way like in our previous examples, by just multiplying the denominator by the square root of 2 plus 1? Let me show you that this unfortunately doesn't work here. So let's multiply by the square root of 2 plus 1 on both the top and the bottom. At the top we get 2 times the square root of 2 plus 2. And at the bottom we get the square root of 2 times the square root of 2. Plus the square root of 2. Plus the square root of 2. Plus 1. The square root of 2 times the square root of 2 is 2. Which is good for us because we eliminated the square root. The 1 is also okay. Because it's a rational number. But the square root of 2 plus the square root of 2 equals 2 times the square root of 2. Which is not what we wanted, because we still have an irrational number in the denominator. So this approach doesn't work. When we have a square root separated from a number in the denominator, like in our original problem. Instead of multiplying the denominator with the square root of 2 plus 1, which doesn't work, like we saw before, we have to multiply the denominator with the square root of 2 minus 1. Why minus? Because we have to use the opposite of the plus sign. By the way, we call this the conjugate of the square root of 2 plus 1. So in problems like this, where we have a root and the number separated from each other, we have to multiply with the conjugate. In other words, we have to multiply with the same expression, but with the opposite sign used in the original problem. When multiplying these two fractions, be careful and don't forget to put parentheses. because you are multiplying the whole expression. So we get with the distributive law for multiplication 2 times the square root of 2 minus 2. The denominator you can solve with the FOIL method or however you want. The important thing is that you multiply each factor in the first parentheses with each factor of the second parentheses. So we get the square root of 2 times the square root of 2 plus the square root of 2 times -1 plus 1 times the square root of 2 plus 1 times -1. The numerator stays the same. The square root of 2 times the square root of 2 is 2. Minus the square root of 2 plus the square root of 2 is 0. And 1 times -1 is -1. So we get 2 minus 1 in the denominator, which is 1. 2 times the square root of 2 minus 2 over 1 is 2 times the square root of 2 minus 2. And we are finally done with this problem. A much faster way to solve this part of the problem is to memorize and use the third binomial, which is a plus b in parentheses times a minus b in parentheses is equal to a squared minus b squared. With this knowledge of the third binomial, we save 3 steps. Aside from this, the 3 binomials are a must-know in math, so I highly recommend memorizing them. I also will make a video on the 3 binomials later. Let's do another example with a similar kind of problem. Now we have 2 separated roots instead of a root separated from a number like in our previous example. 1 over the square root of 3 minus the square root of 2. Again, like in our previous example, we have to multiply by the conjugate of the denominator. Remember, we just take the opposite of the negative sign, which is positive. 1 times the numerator stays the numerator. The third binomial formula says that our denominator is the same as the square root of 3 in parentheses squared minus the square root of 2 in parentheses squared. So we get 3 minus 2, which is 1. We keep the numerator, and after that we divide the numerator by 1, which gives us the square root of 3 plus the square root of 2. And we are done with this problem. What did we learn from the last 2 examples? It doesn't matter if you have a sum of a root and a number, or the sum of 2 roots in the denominator. In both cases, it works to multiply with the conjugate of the denominator to make the denominator rational. Let's do one last example. We have the square root of x minus the square root of y on the top and the square root of x plus the square root of y on the bottom of our fraction. Again, just multiply the top and bottom of the fraction with the conjugate of the denominator, which is the square root of x minus the square root of y to make the denominator rational. I chose this example because we have the second binomial formula at the bottom, which is a minus b in parentheses squared is equal to a squared minus 2ab plus b squared. I also highly recommend memorizing this. So we get x minus 2 times the square root of xy plus y on the top. At the bottom we can apply the third binomial formula and we get the square root of x in parentheses squared, which is x, minus the square root of y in parentheses squared, which is y. We keep the top of the fraction because we cannot simplify it, and we're done with this problem. If you have any questions, feel free to ask me in the comments. This video is what I did for you. If you want to do something for me, hit the bell button, share and subscribe. Thanks for watching and happy learning, everyone.